Hey guys, happy July 4th. This is Mr. Lewitt, your discrete math teacher, and this could be a long video, okay? Well, I'm not sure. I'm not sure. Maybe it's going to be at least 30 minutes. It could be more than 30 minutes. Okay, so here's what we're going to do today. We're going to talk a little bit about prime numbers, but some people in the class have asked me, what is functional programming and why is it a big deal? Okay, so in chapter 4, well, chapter 4 is devoted to number theory, and there's a part of chapter 4 that is devoted to prime numbers. Well, also binary numbers and octal numbers, decimal numbers, hexadecimal numbers, and stuff like that. But for this video, we'll talk a little bit about prime numbers, and I want to try to help you understand one of the advantages of functional programming. Okay, so let me start my terminal. If you use Windows, it's going to be PowerShell. If you use a Mac or Linux, it's called terminal. I think PowerShell and terminal really mean the same thing. Okay. Now, I realize in this class we're basically using Mathematica and occasionally, Haskell, although most of you are probably not interested in learning Haskell. For this video, we're going to use Mathematica, of course, but we're also going to use a little bit of Python. And the reason is because if I show this to you in Haskell, you're not going to get it at all. You're going to get very confused. If I show it to you in Python, I think it will be easier for you to understand. And then after showing it to you in Python, I want to show you something similar in Mathematica and show you the differences. Python is an object-oriented language. Everything in Python is an object, okay? Python is flexible. Excuse me. Python is a flexible language, and it does offer some good support for functional programming. However, in the long run, it's really not a functional programming language. Python is mostly an object-oriented language. Like I said, it offers, some functional features, but it's really an object-oriented language. Mathematica is the opposite. Okay, Mathematica is mostly, not 100%, but it is mostly a functional language. And Haskell, as I have mentioned many times already, is 100% pure functional, which is why it's so elegant. It's a very elegant language, but it's also complicated and not easy to learn, okay? So for this video, we're not going to worry about Haskell. For this video, we're going to worry about Python, and we're going to worry about Mathematica a little later on in the video. Okay, let's start Python. So I'm using my Anaconda Python installation, which begins with IPython. Okay, I'm going to type IPython. Okay, so I'm using Python 3.7.7. It doesn't matter which version of Python you're using. You should use Python version 3. It could be 3.2, 3.3, 3.6, 3.7. I think now they're up to 3.8 or 3.9. Please don't use Python 2. Python 2 is pretty old now, and it's not going to be supported that much longer. If you're going to use Python, you should use version 3 of the language, okay? So let's I need to import a few things here, okay? From the math library, import the ceiling function and the square root function, okay? So what is the ceiling function? Okay, so it's easy. Ceiling of 2.2 is 3. Ceiling of negative 1.9. So what do you think the ceiling of negative 1.9 is? I'm moving up. I'm rounding, excuse me, I'm rounding the number up. Okay, so I believe that's going to be -1. The ceiling of -1.9 is -1. The ceiling of 5.2, I'm going to round up. That should give me 6. The ceiling of -100.9, I'm going to round up. That gives me -100. I think you get the idea. So the answer to ceil or ceiling, it's called the ceiling function. The answer to ceiling is a rounded up integer. Okay? I think, of course, Mathematica has it too. I think in Mathematica it's called ceiling. In every language it's going to be called something slightly different, but it means the same thing. And I think everyone knows what the square root function does. Excuse me. So the square root of 100 is 10. The square root of 81 is 9. Of course, the answer is returned as a floating point number, not as an integer. If you want an integer, you can change it to an integer by doing this. Square root of 81. Okay, and now you get the integer 9. Okay, easy, very easy stuff. This should be very easy for everybody in the class. Now, what is a prime number? What is a prime number? A prime number has only two factors, 1 and itself. Is 5 a prime number? No. I'm sorry, duh, yes, 5 is a prime number, okay? I didn't have my morning coffee yet. 5 is a prime number because the only factors of 5 are 1 and 5. The only factors of 5 are 1 and itself. Okay, is 6 a prime number? What about the number 6? Is 6 a prime number? Well, 6 is equal to 1 times 6, but 6 is also equal to 2 times 3. So therefore, 6 is a composite number. It is not a prime number, it is called a composite number. Composite numbers are simply integers that are not prime. You have prime numbers and you have you have composite numbers. You have prime numbers and composite numbers. Okay, they are mutually exclusive groups. You can't have a number that is both prime and composite at the same time. An integer is either going to be prime or it's going to be composite. It cannot belong to both groups simultaneously. Okay, what about 9? Well, 9 is equal to 9 times 1, right? But it's also equal to 3 times 3, so 9 is not a prime number. What about 13? 13 is indeed a prime number because the only factors of 13, the only integer factors of 13 are 1 and 13, right? The only whole number factors of 13 are 1 and itself. There's no other way that you can get 13. Yes, you could multiply 6.5 times 2, but we're not going to worry about, those decimals and fractions. We're just worried about whole numbers, okay? We're worried about whole numbers, integers, okay? Okay, so how can I discover if a number is prime? So let's think about the number 11. Or maybe let's choose an easier number. How about the number 7? Okay. We all know what mod is. Mod is the remainder of integer division, right? 7 mod 2 is equal to 1 because 7 divided by 2 is 3 with a remainder of 1. Okay, so let's see, 7 mod 2 and 7 mod 3 and 7 mod 4 and 7 mod 5 and 7 mod, sorry about that, 7 mod 6, okay? Well, what do I notice here? None of the remainders are 0. If the remainder is 0, like for example, 7 mod 7 is equal to 0, that's because 7 divides into 7 evenly. There is no remainder. 7 divides into 7, the quotient is 1, and the remainder, of course, is 0. There is no remainder. So if the answer to mod is 0, okay, that means I found a factor of the number. For example, 10 mod 5 is 0 because 10 divided by 5 is 2, and there's a remainder of 0. Why is there a remainder of 0? Because 5 is one of the factors of 10. And because 5 is one of the factors of 10, I know that 10 cannot be a prime number. Okay, because if 10 was a prime number, I would never get 0. So this is what I'm talking about. 10 mod k for k in range 2 up to 9. Now Python is funny. If I want the integers 2 to 9, I have to specify the range 2 to 10. 2 to 10. So here's what I'm talking about. And Python can be a little weird that way. If I want all the integers from 2 to 9, then 10 has to be my upper limit. Okay? Okay? Then 10 has to be the upper limit. It's always going to be one more than the last integer. Okay, so 10 mod k. Here, 1 second. I just want to turn off pretty printing because I do find it a little bit annoying. Okay, so 10 mod, I'm going to use the letter k. Use whatever letter you feel like using. For k in range 2 to 10, which really means the range of integers from 2 to 9, by the way. Okay. Do I see any zeros in that list? Yes, I do. I see zeros in that list. In fact, let me make this a little bit more clear for you. Maybe you'll be able to see it a little bit better. Oh, what is the problem here? Oh, I see. Oops. Hold on 1 second. Sorry about that. Okay. So I see that 2 is a factor of 10 because 10 mod 2 is 0. 3 is not a factor of 10. 4 is not a factor of 10. 5 is a factor of 10 because 10 mod 5 gives me 0. 10 mod 6 gives me 4. I know 6 is not a factor of 10. 7 is not a factor of 10. Neither is 8. Neither is 9. It just takes 1 0 to disqualify an integer from being a prime number. Based upon this, I can write a nice little function that will generate prime numbers for me. So let's give this a whirl. Okay? Let's give this a whirl. How should we do this? We're going to start with define. Oh, by the way, I'm going to use filter. How does filter work? Filter, lambda, I'm going to choose a letter x. I just want even numbers. And let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there we go. So filter is a really nice command in Python. And I can use it to filter elements out of a list. So what did I do? I filtered out only the even numbers because, of course, if a number is even, that number mod 2 has to be equal to 0. Okay? If I want the odd numbers, then of course this is going to be the number 1. Okay. All right, so based on that, I can write a nice function that's going to help me do this. But I need two functions. Let's give this a whirl. So my computer's fan is going strong. I don't know why that is. That's weird. Okay. Anyway, let's get moving with this. So define. I'm going to call it primes helper. And I'm going to have a start, I'm going to have a stop, and I'm going to have a primes list. Okay. If start is greater than stop, return list primes list. If you don't understand all of the syntax right now, don't worry about it. Don't worry about it, because basically for this course you really need to worry about Mathematica. We'll go to Mathematica in just a few minutes, but there's a reason why I'm showing you Python, and that will become clear to you in a few minutes. If start is greater than stop, return primes list as a list, else, let me see, new primes list is equal to filter lambda, I'm going to call it x, or you can call it whatever, give it any letter you want. X is less than or equal to start, or x mod start is not equal to 0. Primes list, return return primes helper, start plus 1, I'll make that look a little prettier, stop, new primes list. Okay, and that looks really good. Now my next function is going to use the primes helper function. Okay, so define the function primes, and I'm going to have some number. Okay, and let me see. K for K in range, start with the number 2, and I want the last number in my list. I want the last number in the list to be number, so this has to be 1 plus the number. And this is my initial list. And then we're going to do return primes helper. We're going to always start with 2 because that's the first prime number, and this will be ceiling square root of the number, because when you're searching for prime numbers, guys, you can really stop at the square root of the number, but the square root of the number is usually a decimal number, so ceiling turns it into the next integer, and then we're going to have our initial list. Now let's see if this works. Primes 100, yeah, that looks pretty good. Primes 1000, hold on 1 second, why? Okay. That's fine. Okay, primes 5000. Yeah, this is actually working out pretty well. So these are all the prime numbers up to and possibly including 5000. Okay? And these are all the prime numbers up to and possibly including 1000. And these are all the prime numbers up to and possibly including 100, etc., etc. Now, here's the point that is very, very important for you guys to understand. Oh, and let's go to maybe 10,000. My primes list is equal to primes 10,000. So this is what my primes list looks like. These are all the prime integers up to and possibly including 10,000. Okay? That's my primes list. Now, what if I want to make a backup copy? My primes list 2 is equal to a copy of my primes list. Make a backup copy just in case I screw up the original list. Okay, so now I have my primes list and I have my primes list 2. And they should both be the same, right? Now there's a problem here. And the problem is this. Let's say that I make a change to my primes list 2. My primes list 2 is equal to hello world. So my primes list 2 now has hello world at the very beginning, right? But what about my backup list? What about my backup list? My primes list, it also has hello world at the very beginning. So whatever changes I made to my copy also happened to my original backup list, and that's exactly what I don't want. Whatever changes I made to the copy, any modifications I made to the copy, they also took place in the backup list, and that's exactly what I do not want, right? So this is one of the biggest problems with object-oriented programming. Okay, with object-oriented programming, you have to be very careful about making copies. Okay, that is a real issue. In fact, that's a major source of bugs in most object-oriented software. Okay, I didn't want hello world to show up in the original list. I only wanted hello world to show up in the copy. My primes list 2 is a copy. But hello world also showed up in the original list. And the reason is because my primes list 2 is not really a copy at all. It's an alias. It's an alias. It's not a copy. And this is a big problem with object-oriented programming. And of course, there are solutions, but sometimes the solutions get complicated and messy. Okay, let's turn to Mathematica now and see how Mathematica in some ways is actually easier to use than Python. Okay. One second. All right. Okay, so let's turn to Mathematica. Okay, let's format this so it looks a little nicer. Input, output. Make this a little bit bigger. Make that a little bit bigger. And let's see, text color. Make that a dark blue. And we could make that make that a dark blue, and then the background, let's make that how about a light green. Okay, so we're going to do the same thing now in Mathematica. I'm going to kind of go through this a little bit faster because this video is getting a little bit longer. It's getting a little too long, okay? It's getting a little longer than I would like it to be, so I want to start wrapping things up. So I'm going to go through this a little faster without, you know, constant detailed explanations of every single move, okay? So let's see. My primes helper function is defined like this: start, stop, primes list. If start is greater than stop, give me back my primes list. Otherwise, let me see. My new primes list is going to be cases, which is like filter, primes list, and I'll say x is less than, oh, wait 1 second. Oops, wait a second. Primes list, there has to be a comma here. X is my variable. X is less than or equal to start, or, that's the symbol for or, mod of x start is not equal to 0. Semicolon. Recursively call the function primes helper, start plus 1, stop, new primes list. So let me make sure this is okay. 1 second. Start is greater than stop. Give me back the primes list. New primes list. We filter out the numbers we don't want, which are the composite numbers. I think this looks good. Let me shift enter. This looks okay. And then primes. Let me test one thing here. Hold on 1 second. Ceiling of 2.3 is 3. Ceiling of 3.1, 4. Ceiling of negative 1.2 should be negative 1. Okay, we're good. Okay, so primes primes number. Okay, so this, I'm going to declare a module here. Initial list is equal to range from 2 to the number. Not in Python, you would do number plus 1. Number plus 1, but in Mathematica, it's just going to be number. Okay. Close my list. And then here we are going to do primes helper. Start with the first prime number, which is 2. This will be ceiling square root of the number. And we're going to start with the initial list. Notice, by the way, and this is important, Mathematica does have a return keyword. Okay, Mathematica does have a return keyword. Honestly, it's not really used that much. It's not used that much. In object-oriented programming languages, the return keyword is used all the time. It's used a lot. It's a big deal. In functional languages, it's either not used at all or it's used only occasionally. Okay, Mathematica does have the return keyword. It is not used a lot. Okay, and Haskell doesn't even, well, Haskell actually does have return, but it's very different from the return in Python and Java. It means something totally different, which I'm not going to get into in this video because then you'll get totally confused. Okay, so this function looks pretty good. Give me all the prime numbers from 2 to 100. Okay, that looks excellent. Primes, give me all the prime numbers from 2 to 1,000. Let's see. Okay, terrific. Now here's the interesting thing about Mathematica. Okay, so my primes list is equal to primes 1,000. Okay, terrific. My primes list 2 is equal to my primes list. Okay, so is my primes list 2 an alias or a copy? In fact, let me write that down over here as a comment. Is my primes list 2 an alias or a true copy of the original my primes list? And there is a difference between an alias and a copy. There's a big difference. So I have my primes list and I have my primes list 2. Okay, so let's see something. My primes list 2 is equal to hello world. My primes list 2. Okay. So I replaced the 2 with hello world. What about the original list? My primes list. Notice that I still have 2 here. The 2 was not replaced with hello world, which means the answer to this question is very simple. My primes list 2 is a true copy of the original my primes list. It is not an alias. It's not a reference to the original list. It is a true copy of the original list. So the big takeaway here is, in a functional programming language like Mathematica, Mathematica is mostly functional, not 100%, but it is mostly functional. In a functional programming language like Mathematica, okay, copies are really copies. In a language like Python, Python offers some support for functional programming, but really Python was originally designed and is still designed to be mostly an object-oriented language. In an object-oriented language, like Python, for example, you have to be very careful because oftentimes you think you're copying an object. You're not copying the object at all. You're simply declaring a reference to it or an alias for it. There is a big difference between an alias and a copy. There is a big difference between an alias and a copy. Copies are independent. Aliases are not independent, and that really is a big source of many bugs in programs. Okay? I know we covered a lot in this video. I think this was a little bit complicated for you guys, but hopefully you did learn something useful from it. I'm sure some of you have experimented with Python. It is a dynamically typed language like Mathematica, but it's an object-oriented language. Mathematica is not object-oriented. Mathematica is functional. And there are differences. Object-oriented programming and functional programming may look similar on the surface, but actually they're very different. They're very different. Okay, I really think that's enough for now. I think that's I've given you guys plenty of material to review and digest. Good luck with your midterm exam, and as soon as possible, please get to work on Chapter 4. Chapter 4 covers a lot of very complicated stuff, including prime numbers, but there's other stuff in Chapter 4 as well. So we still have a lot to do before July 30th. July 30th is, of course, the last day of our course, and we still have a lot of material to cover before this course finally ends on July 30th. And yes, there will be one more There will be one more Mathematica programming assignment, and there will be an extra credit Haskell assignment. And yes, I am going to post a couple more tutorial videos on basic, simple basic programming in Haskell. Okay, Haskell is really cool. Haskell is a very, very, very cool language, but Haskell is not an easy language to learn. But I would like to expose you to it because Haskell is a wonderful programming language for people who are interested in very serious, high-level mathematics. Okay? Okay, that's it for now, and I think we're done. Have a fantastic July 4th holiday. Bye-bye.